sharing. Laura, would you like to share your screen?
Sure, can you guys see it?
Yes, we see it and we hear you.
Okay, let me turn on my video too.
Okay, while you do that, our next speaker is Laura Hiatt. Laura, you go ahead.
All right, so hi, thank you. I'm happy to be here today. And I'm going to be talking today about work that we've done on using cognitive models to train big data models with small data. And the types of models that we're talking about here are models of human behavior. So the reason why we are interested in this topic in general is there are a lot of benefits to modeling and predicting human behavior. And I know I'm kind of preaching to the choir here. For us, one of the reasons that we focus on it is it improves the quality of human-robot or human-AI interaction. And it also can improve the overall abilities of the human-robot or human-AI team. And those are something that we care a lot about. And there are a lot of different modeling techniques that capture different facets of this modeling and prediction problem. Some focus on different timescales, like we heard about this morning in John's talk, or they can handle different types of observations, etc. The two classes of models that I'll be focusing on today are cognitive process models. ACT-RE is the one that we use. It's a derivative of ACT-R, and statistical models. So cognitive process models, again, I know I'm preaching to the choir, but they capture the internal processes of human cognition. And importantly for this talk, they capture very explicitly some of the noise and variance of human cognition. These are usually descriptive models, and there's fairly small data requirements for developing a new model of a task, in large part because so much data has gone into developing the encompassing architecture. Statistical AI models, though, like convolutional neural networks and other deep learning or machine learning approaches, they don't know anything about human cognition. They just learn a mapping between outward observations or whatever data they're given and a label. And so because of this, they're very strong predictive models, and that predictive power can be very useful for human-robot or human-AI interaction. But the cost is that they have a very high data requirement. Again, because these models have no prior understanding of how people or the tasks that they're working on go, or even what observation features to pay attention to, they need to learn it all from scratch, and that can take a lot of data. And just to highlight this further, the data requirement of these models is so high that gathering, labeling, etc., enough human empirical data to train an approach like a convolutional neural network is just not feasible. There are collection issues. I mean, just having that many participants go through your lab could take a long time. There are labeling issues. You can't outsource labeling of much of this data to Mechanical Turk, for example, because the MTurkers don't have the right expertise to label some of the types of human empirical data that we deal with. And there are balancing issues. You guys are going to hear me talk about variability a lot through this talk, but people's behavior is very variable, and we need to make sure that our data reflects the correct distribution of that variance, and it takes a lot of data to do that. So an example of how long it takes to collect human data, we collected 200 traces of human performance on a short supervisory control task, and it took about 80 hours to collect, extract, verify, and label all that data. So if we extrapolate that to the roughly 60,000 examples in MNIST, which is a fairly standard machine learning database, it captures handwritten digits, that 80 hours turns into 24,000 hours, which a back of the envelope calculation can tell you is about 11 and a half years of one person working 40 hours a week with no vacation. So this is just not feasible. And this isn't even touching what would be required to get the equivalent of the 14 million images that are in ImageNet. So this is a challenge. Using these models on human behavior is a challenge. But we're optimists, and we really want to be able to have our cake and eat it too. So we really want the predictive power of the statistical AI models while kind of getting or just leveraging the small data requirements of cognitive process models. So we're going to leverage the strengths of each of these in order to build effective predictive models on human behavior without large amounts of data. So we're going to use the cognitive process models built with small data to generate synthetic big data. And then we're going to use, give that big data to the statistical AI models to consume to give us the predictive models that we're looking for. And this is really, just to really make this explicit, this is the crux of this work, to build the better AI models of human behavior with the small amounts of empirical data that it's realistic to collect. And this is work that's related to what Greg presented earlier. You'll see a few things here that might look familiar, but I want to make sure to point out that the purpose of this work is fairly different. So while in Greg's talk, he highlighted our work focusing on the combination of machine learning and cognitive process models in order to validate the process models, and the machine learning was a tool to accomplish that. In this work, we're focusing on using the combination of AI and cognitive process models to build better AI models, and the cognitive model here is the tool. So, and in fact, in that way, this talk may differ from some of the other talks here, since we aren't really focused on improving the cognitive models or architectures, but we're focusing on leveraging their current abilities. So looking what our data or workflow pipeline would need to be to accomplish this, well, we have a task. We have built a cognitive model of that task based on what we know about it, and maybe peeking at some of the data that we can collect on that task. Then both the task and the cognitive model collectively give us data of human performance on that task, both empirical and synthetic. Then we can take that data, train a machine learning model or other statistical AI approach on how people act when they're performing that task. And then given that, we can then feed, human performance and get a prediction of the human's next action, and leverage it in whatever way is convenient for that task. So now that I've kind of talked about the overall picture, I'm going to delve more into the technical parts of this and describe each of these components one by one. And I'll go through them by grounding them in the specific tasks and models that we use, but really the contribution here is the overall methodology. We're not limited to this one task or this one cognitive model or even cognitive architecture. So the task we use is a rescue task. You saw some of the details of this earlier, again, when Greg talked about the orthogonal aspect of this work, but I'm going to quickly go over it again, since that was like an hour and a half ago and it was before lunch, which everyone knows resets your brain. So the rescue task is a supervisory control simulator where there are multiple UAVs that fly around. They have to get to targets, and there are hazard areas that damage the UAVs if they fly through them. And the hazard areas kind of change periodically. There's also a visual task that humans need to perform when the UAV reaches a target. And again, as was said earlier, there's a lot going on. You have to track the UAVs to see if they need help. You need to pick new targets for the UAVs if the current target is not appropriate anymore, etc. And here, as before, we're focusing on this subtask of this overall supervisory control scenario where we need to reroute the UAV. So here is the video of that happening. So it's moving the UAV to this target here. And so if you were watching where the eye gaze was moving, the eyes were looking kind of all over the place as they were doing this. There was a lot of noise in their eye gaze. They weren't just looking at the target, the UAV and clicking on it and then looking at the target and clicking on it. They were looking at other UAVs, they were looking at hazards, multiple targets, all before they selected the UAV itself. And then they looked at some more different hazards and targets before they selected the final target to send the UAV to. So again, there's a lot of variance here, even though this was a skilled operator performing this task. So there would be a high data requirement in order to have enough data to really train like something like a CNN to adequately predict behavior in this situation. And the finals, just to highlight again, the final selection of what they did is target A, and that's what we're looking to predict in this particular task. What target will the person ultimately send the UAV to? And predicting this final action could help with automated assistance, for example. If you knew it far enough in advance, you could pre-select the target or perhaps suggest a better destination. So there is a lot of utility in tasks like this with understanding what a person is going to be doing and predicting their behavior. And I'll just show the video one more time so you can really look at the noise of everywhere that the person is looking. Okay, so now moving on to the cognitive process model. We use ACT-RE, but really this could be theoretically done with other architectures as well. And unlike Greg's use of strategies, if you remember his talk, he talked about the opportunistic and planning strategy. His use of strategy was to evaluate the goodness of any given model, of any given strategy in capturing people's performance. But here, we want to include models of multiple strategies because we want to make sure that our synthetic data includes all this wonderful variability of human behavior that I keep emphasizing to make sure that we learn a good statistical model of human performance on this task. And so I've listed here again the opportunistic model, where you look for a UAV that needs a target, you select the UAV, you look for the target, select the target, etc. And our models of these strategies included all of the visual actions and memory retrievals and goal structures, etc., in order to make this happen. And just to really close the loop on that, we use the default parameters for this model, including activation noise, as well as some production level competition. So there was some variability within the models as well, not just between the strategies. So now that we have the model, we can start getting synthetic data from it. So ACT-RE models, as they execute, very conveniently and naturally generate output traces of the same type as the empirical data. So it can output what its eye fixations are, the model, as well as where the mouse is clicking. And these traces are also labeled for free because the model knows as it's running what it's doing and why it's doing it. So it knows, for example, that in this segment of eye fixations and mouse clicks, it's looking to switch a UAV and it's going to switch it eventually to target A, for example. That's a kind of a simple label, but this applies to more complicated tasks and labeling schemes as well. And since this is a computer program and not a person, we can run it faster than real time. So, it really doesn't take that long to generate many traces of this synthetic data here from these models. Okay, so we have a task, we have a model that can generate data. So now moving on to the statistical AI model. We use a convolutional neural network here again for prediction. As I've said, and as Greg said, these are very strong predictive models when they're given enough data. The input of the model was a vector of eye fixations and actions leading up to that final target selection. And then the label, or during testing, the output of the model was the predicted target selection that the person was going to move the UAV to. And there are various layers here. There's details in the paper of how we set up the model and why we chose this particular model to use. And I have a link to the paper that we wrote on this at the end of the talk. Okay, so now I've described all the components of our workflow and methodology. Hopefully it's clear here how everything kind of comes together to build these these statistical predictive models of human behavior. So let's switch now to talk about evaluation and how we know when we're doing a good job. So there's kind of two questions that we want to answer when we think about how good this methodology is. The first one is, does the synthetic data generated by the cognitive process models exhibit the same key characteristics, and by that I mean variance and distribution, et cetera, as the empirical data of people executing the same tasks? And the second is, can statistical AI models trained on synthetic data be used to predict human performance on the task at hand? So do we have the right data, and can we use that data in order to train a good predictive model? And we can really answer both of these questions by training up some convolutional neural networks and see how well that they do predicting human actions when trained on the synthetic data. Just to make very explicit the data that we have available to test out this approach that we'll be using here, for empirical data, we have data from 10 participants that are performing this rerouting subtask of rescue. They were all volunteers. They did some training, and then they interacted with the simulator to perform the task. Obviously, eye tracking and mouse clicks were recorded. Those provided our data points. And we have 200 traces available of those 10 people performing this subtask. For the synthetic data, we generated 20,000 traces of from the planning model and 20,000 from the opportunistic model. And these were really generated in negligible time. And again, this doesn't make any claims about what strategies are right or wrong. That's kind of Greg's side of the coin that he spoke about earlier. This is more about just getting enough data variability of the things that people are doing in order to make sure that our overall data that we're using to train the model captures the richness of human behavior. Okay, so with this data, we trained 7 different CNNs in a variety of conditions. So we had an empirical baseline where we trained using only the empirical data. So half of it was used for training, half of it was used for testing. We had a planning condition where we trained using only the planning synthetic data, opportunistic condition where we trained using only the opportunistic synthetic data, combined where we trained half on planning and half on opportunistic. We kept the same number of traces the same for that condition though. And then we repeat the following 3 while also throwing in some of the empirical data into the training. And so for all models, we use cross-validation to divide the data into training and testing data. And all of these models were evaluated only on empirical data. Okay, so the first bar that I have here is this baseline empirical. This is the statistical model that was both trained and tested only on the human empirical data. And it got about 40%. So, you know, not great, but at least it's better than 2 other simple heuristics that we looked at. So two other ones we looked at were the UAV that was looked at last, just before doing target selection. And that had about a 30% accuracy at predicting the ultimate target. And then the UAV that was looked at most, and that was not as good. That it got about a 23% accuracy. So it's better than nothing, but it's not that great, which is not surprising given how few data points there were for training this model. The next 2 bars here show the planning models. So a CNN trained just on planning data, and a CNN trained with planning data and some empirical data. And since Greg's work earlier suggested this was a viable strategy, what the low accurate or comparatively low accuracy on this tells us is that this strategy alone just does not capture enough of the variance of human behavior to build a robust classifier. So we need to do more about that. Next is opportunistic. This is quite a bit better than planning. And that tells us that perhaps because this strategy, as we've kind of talked about a couple times, has a bit more variance because you're looking around a little bit more. You don't quite have your mind made up to the last minute. It introduces in that meaningful variance that people exhibit. But really the best comes when we combine both. So these last two bars show the results when we have data from both strategies that's used to train the CNN. And then the last bar here is actually when we have both strategies plus a little bit of empirical data. And that little boost of the empirical data, what that tells us is that we're still missing a little bit of the variability of human performance in our collective data pool. But since the boost isn't too big, we're actually pretty close. So we're doing a pretty good job, both by having the strategic variance and by having the within model variance, you know, with that activation noise, et cetera, at capturing what people are doing on this task and what's going on. We also, just for fun, trained a naive Bayes classifier. This is a type of statistical model that can perform better on limited data than a CNN can. So we wanted to see how we did on that. And it got about 55%. So not as good as the models, the CNNs that we trained with the synthetic data. Okay, so moving to the discussion part, our approach addresses these several concerns in data that I brought up earlier. I mentioned collection issues. Well, using synthetic data to augment empirical data can turn these impossible models into successful ones because we don't have to actually collect it. We can just click a button and the computer can generate it all while we take a nap. Labeling issues, these process models allow us to automatically label the synthetic data, so we don't really have labeling issues anymore. And balancing issues. So the limited empirical data is just not enough, as I've said, to represent the full distribution of human behavior, but by generating this synthetic data, we're able to capture and represent more of the distribution in our data set. And then returning to these evaluation questions, the goals of the evaluation that I mentioned earlier. So one, does synthetic data generated by cognitive process models exhibit the same key characteristics as empirical data of people doing the task? Well, it seems like it does, as long as we have both of those dimensions of variability in the process models, the different strategies that people use, as well as that internal model variability. The second question, can statistical AI models trained on synthetic data be used to predict human performance of the task at hand? Yes, you know, again, results are good. I also added a part B of this question that hints towards some of our future work. We're also interested in whether these statistical AI models can be used to better understand the overall task structure. So if we can get enough data from them to, for example, learn the structure of a hidden Markov model or a hierarchical hidden Markov model, then that might tell us more about, you know, what strategies are going on or how people are conceptualizing these tasks, et cetera. So just to summarize, our methodology that I talked about today combines a process model of human cognition with statistical AI model to better predict human performance. And we combine these two by generating arbitrarily large amounts of diverse synthetic human data and using that to train the convolutional neural network to predict human performance. And then at the bottom here is the reference to the Amos paper that I mentioned earlier with many more details of this work. So with that, I'm happy to take any questions.
Thank you. There are a lot of questions. I'm going to try to take them in order.
Okay.
First, why are predictions from statistical AI better in comparison to cognitive models? Is it because statistical AI is better able to generalize to unseen data points?
I think that's partially it. It's able to gloss over things like blips in the eye tracker, for example, much better than I found cognitive models to be able to do. I mean, I have done some work kind of tracing through a cognitive model as someone executes the task, But if the person goes off script, there's just no good solution for recovering from that. Whereas because the statistical models are kind of matching just the most likely behavior, the most likely label, they don't care if it's not a perfect match. If the person goes off script here or there, you know, that's going to be okay. Kind of like an image getting blurry, right? But a CNN still being able to recognize it.
Okay, thank you. So the next question is, what is your meaning of descriptive and predictive? Because this person would characterize statistical AI models as descriptive because they solely reflect the data with which they were trained, and cognitive process models would be predictive because they can leverage their constraints and mechanisms to generate predictions for situations for which there is no data.
Yeah, so I would agree with that characterization, but the way that we mean descriptive and predictive here is cognitive models are descriptive because they're describing what's actually going on under the hood. So they're kind of describing the process that people go through, which statistical AI models just are a complete black box about. And for predictive here, we're basically using the classifier as a predictive classifier. So, you know, given the current situation, what would we predict it do next? And to do that, we're using, again, using the classifier to kind of bin it into that next action.
Okay, so our next question is wondering about if you could be doing more with the combination of cognitive model and statistical model, such as using the cognitive model to inform and guide the learning of the statistical model, I'm assuming. Such as you don't need to learn in situations where the cognitive model is actually sufficient to process the data. That would make the statistical model easier to learn. And there are a few other examples here. So it basically, is there more that you could do to have one model help the other and vice versa?
Oh, absolutely. Yeah. I mean, this is our first, this is probably the first step of many. There's a lot of interesting things you can do here. So there's a lot of work right now that's looking at how to incorporate physics and other types of knowledge into learning statistical models and guide their learning so you can learn them more effectively. We haven't looked into that, but that's something you can do here. Like if the cognitive model suggests a particular manifold within the data, for example, maybe you could constrain the parameters of the statistical model to only search along that manifold. Another example is, you know, going in the other direction. And this relates to, I think, what Greg was talking about earlier. If a CNN that we train with based on data from a particular cognitive model just is not working, then that might in turn suggest that there's something wrong with the cognitive model, and maybe we should revisit that. So yeah, there's absolutely more that we can do here. This is just what we've gotten done so far.
Thanks. So next question was, how do you evaluate that the statistical model is capturing constraints similar to those in the cognitive models? And is that an important research question for you to answer?
Yeah, so we're really only evaluating that implicitly. We haven't, you know, we're generally treating the statistical model as like I said earlier, kind of a black box. So we're not peeking under the hood and looking maybe at that last layer to see what features it's picking up on. That's not something that we've done yet. We've just implicitly said, well, if we build this statistical model and it does a good job on the human data, then something went right? Then presumably the constraints and the theory and the richness from the cognitive model got transferred into the data, and then that made its way into the statistical model. I mean, there are some caveats to that, though, of course. You know, one can imagine tasks where the observations just don't really match up with the final action, and maybe that's just the nature of the task. And in that situation, I would argue that statistical models aren't going to get you that far because they're just not really going to have anything to work off of. And so they're not going to be able to incorporate in the important features of the cognitive model. But for tasks like this, where the observations that you can get do seem to closely align with the mental processes going on, then I think this implicit comparison, at least for now, is good enough.
Okay, thank you so much. There are a lot more